Hello everyone, and welcome back to the class. For new rules, is I, your host, ichino-ani, ready to explore another amazing paper with all of you. Today is Monday, March 30th, 2026, and we have a very exciting topic from the machine learning archives. Right, so today we are going to talk about a paper titled Unified Memory Perspective for Probabilistic Trustworthy AI. You can find this fascinating read at the crawl. archive.org/abs/2603.25692v1. I know it is quite a mouthful, but I promise the ideas inside are super cool and easy to understand. Let us dive right in, shall we? The main problem this paper is trying to solve is something we call the entropy wall. You see, artificial intelligence systems today are doing incredibly important jobs, and we need them to be completely trustworthy. For an AI to be trustworthy, it cannot just give a single rigid answer. But it must also understand uncertainty, explain its decisions, and protect our privacy. To do all of these things, the AI relies heavily on probability and randomness. It needs to generate and use a massive amount of random numbers, which we call stochastic sampling. Right, so here's the tricky part that the researchers discovered. In our standard computers, which use something called the von Neumann architecture, the part that stores data and the part that generates random numbers are totally separate. So when the AI needs to think about uncertainty, it has to constantly ask the random number generator for new numbers, and then bring those numbers all the way over to the memory in processing units. This creates a huge traffic jam. The paper points out that while computer processors have gotten super fast, and memory can hold lots of data, the random number generators are just too slow to keep up with the demands of modern AI. Let's dive a bit deeper into the science behind this traffic jam, shall we? The authors of the paper introduced a very clever concept called the Probabilistic data ratio. Data ratio, which they simply call alpha. An alpha basically measures what fraction of the computer work is just asking for random numbers, compared to asking for regular, fixed data. If alpha is 0, the computer is just doing normal tasks, like opening a document or reading a saved file. But as the AI tries to be more trustworthy and understand uncertainty, the alpha value starts to grow. The researchers built a mathematical model to show that as this alpha value increases, the entire system shifts from being limited by the memory bandwidth to being limited by the random number generation speed. This is what they call hitting the entropy wall. It is exactly like trying to fill a massive swimming pool using a tiny little garden hose. No matter how big the pool is, the water can only come out as fast as that tiny hose allows. Even if only 1% of the tasks require randomness, the whole system slows down, creating what the authors call an entropy-limited operation. But do not worry, because the paper proposes a brilliant solution. They suggest a new way of building computers called probabilistic computed memory. Instead of having a separate random number generator far away, they want to build the randomness right into the memory itself. They introduced a unified data access perspective. This means the computer treats normal fixed data simply as a random sample that has 0 variance. So whether the AI needs a fixed number or a completely random one, the memory handles it all smoothly in one single place. And this completely removes the traffic jam, allowing the AI to run much faster and more efficiently. Now let us compare this with the older technology, like in traditional computers. Making a random number requires running complex math formulas, or using special external hardware, which takes extra time and uses a lot of energy. But with probabilistic modeling, the system uses the natural physical noise of the memory chips themselves, like tiny temperature changes or microscopic electrical variations, to generate randomness instantly and naturally. It is like having a magical box that gives you exactly what you need, without having to run to the store every single time. Right, to fix this garden hose problem, the paper discusses 2 flavors of this new memory technology. The first flavor is called coupled probabilistic computed memory. In this setup, the place where the computer stores the data and the physical mechanism that creates the randomness are literally the exact same tiny device. And this is incredibly fast and saves energy, which is perfect for AI systems that are hungry for randomness. However, the paper notes that because they are glued together so tightly, it is very hard to control the exact shape of the randomness. It is like having a paintbrush that only paints in one shade of blue. So to solve that limitation, the researchers also explore a second flavor, called the probabilistic computing memory. The normal data storage and the randomness generator are kept slightly separated, but they still live right next to each other inside the memory chip. This gives the computer scientists much more control over the distribution of the random numbers, allowing them to shape the randomness to perfectly match whatever complex math the AI is trying to do. It takes a tiny bit more energy than the coupled version, but it gives the AI a full palette of colors to paint its brilliant, trustworthy decisions. Right. So how does this actually help us in the real world? The paper mentions several amazing applications, and I want to share 3 specific examples where this technology will make a huge impact on our everyday lives. Let's first think about medical decision-making, especially things like continuous glucose monitoring for people with diabetes. The human body is very complex, and medical readings can be noisy or unpredictable. By using Bayesian neural networks, which rely heavily on randomness to calculate uncertainty, the AI can look at a patient health data and confidently say, "I'm 80% sure their sugar level will drop, but there is a 20% chance it will not." With the new unified memory technology from this paper, these life-saving AI models can run constantly on tiny, low-powered chips, maybe even inside a wearable smartwatch, but without draining the battery or slowing down. This means patients get faster, more reliable health warnings when every second counts. For our second example, let us look at autonomous driving and robotic agents. Imagine you are riding in a self-driving car, and suddenly a stray ball rolls into the street. The car AI needs to react instantly, but the real world is full of unknowns, like whether a child is running right behind that ball. To make a safe choice, the AI runs Monte Carlo tree search, simulating thousands of possible futures in a split second using random sampling. If the car uses an old computer, the traffic jam of random numbers might cause a dangerous delay. But with probabilistic computing memory, the car can generate those thousands of random scenarios instantly, allowing it to hit the brakes exactly at the right time, making our roads incredibly safe for everyone. And for the third example, let us talk about keeping your private information safe on the internet. When large companies train the AI models on our personal data, we want to make absolutely sure they cannot trace that data back to us. A great way to do this is by injecting controlled noise, or randomness, directly into the learning process. This is often called privacy-preserving artificial intelligence. Because this new memory technology handles random numbers so effortlessly, our phones and personal computers can easily scramble our data before sending it out, without slowing down our devices at all. So you get to use super smart AI tools. And your personal photos, messages, and searches stay completely hidden and protected. It is just so wonderful to see how thinking differently about hardware, like bringing the randomness directly inside the memory, can solve such massive problems. Other researchers from the University of Notre Dame have lately shown us a clear pathway, moving away from the old separated computing methods and guiding us towards scalable, trustworthy AI for the future. By turning random physical noise, which used to be seen as a bad thing, into a powerful tool for computation, we're stepping into a whole new era of technology. Well, my dear listeners, that is all the time we have for today's class. I let you enjoy that. Remember, sometimes the best way to solve a difficult problem is not to just build a faster car, but to completely redraw the map. Keep asking questions, and always stay curious about the world around you. And I will see you all in the next episode.